Good. Hello, everyone. Pat Zemer here with Magna. Thank you very much for joining us today. Today we're going to have a few people with us on the phone call, but our primary guest is Dr. Robert Dennis, Bob Dennis. He's a PhD. He's going to tell us a little bit about himself and how he became involved in the PEMF and studies that he performed for NASA. And I think that's a great question because people always ask about what kind of research has been done, what the results have been, and how that all plays out. So we'll get with Dr. Dennis here in just a moment. Also with us this morning, if you have questions, simply put them in the chat box and we'll get right to them. As you know, we like to keep these calls to about an hour, so we'll answer every question we can as we move along. Also with us today is Dr. Jerry Dreesen, chiropractor from Seattle, Washington, and a Magna Wave Max user in his practice. And so he may have some questions as to how it applies to what Bob Dennis is discussing. And also with us is Michael Davis, the manufacturer of the Magna Wave Max, and he may have some input for us as well. So thank you all for being with us. Thank you, those in the audience, ladies and gentlemen, for being with us. And at this point, I'd like to introduce Dr. Dennis and kind of ask you, and he said he prefers to go by Bob. So Bob, tell us a little bit about your background, where you are today, and how you got involved with NASA and the study, and some effects of that. Thank you.
Absolutely. Thanks for inviting me, Pat. My background is actually a PhD in biomedical engineering. I'm essentially a medical device designer, and my research is in tissue engineering. So I do a lot of research on how to build devices that grow tissues in culture and inside living animals. And this includes a lot of different tissues. I've published in areas of skeletal muscle, cardiac muscle, smooth muscle, vascular, bone, ligament, tendon, articular cartilage, a few other areas. So I'm pretty widely published in tissue engineering, probably 40 or 50 papers in that area. I'm currently at the University of North Carolina as a professor of biomedical engineering. I started out at the University of Michigan, which is where I did my PhD and started doing research. Had a lab at Michigan for a while, and I was also in the Harvard MIT Health Sciences and Technology program, HST program, where I had a laboratory in the Artificial Intelligence Laboratory at MIT for a number of years. So now I'm at UNC, but I do a lot of research outside the university because, in my opinion, academic research is great for what it's great at, and it's limited in other ways. So I've always done a lot of consulting. In fact, I've been consulting a lot longer than I've been in academia as a professor, and that's kind of where NASA comes in. I'm a classically trained scientist. I actually did my PhD not in an engineering lab, but in a physiology, cell biology laboratory. So I had a consulting company, and I got a call in 1996, at the end of the year, beginning of 1997, to ask if I would help some people at NASA Johnson Space Center develop a system for cell culture for microgravity. And I said, okay, that sounds interesting. What would you like to do? And they said that they would like to apply time-varying electromagnetic fields, TVEMF, which is the abbreviation you see on all the NASA patents and publications. They don't call it PEMF, they call it TVEMF. And they asked me if I would help them design a system for applying time-varying electromagnetic fields to cells in culture. And I said, okay, well, I don't really think that does anything, so let's talk about it first before we spend a lot of time and money. Why do you think it would work? Was the first question I asked them. Do you have any data? They said, no, we don't even know where to start. I said, okay, what are you trying to accomplish? And they said that they would like to be able to modulate gene expression for cells grown in culture. And I said, okay, that's reasonable. And at that time is when the new gene array technology was just coming out in the late 90s. So you could actually do gene array analysis and say things, important things about what cells were doing and how they were changing if you were doing even pretty subtle things to them. So I said, okay, well, we have a good biological model. They're very good at cell culture at NASA. They have these rotating vessels where they can grow cells, and they can do a lot of good science at Johnson Space Center. So I said, sure, absolutely, I'd be happy to take part. However, the condition is that, we do this strictly by the book, and we do really well-controlled science to the highest standard. Because I told them, I'm at the beginning of my career, and I can't really be involved in something that's sort of, pseudoscientific. If we're going to do this, let's do it as well as we possibly can, which includes a carefully designed study, carefully calibrated devices to do the study, double-blind controls, all the sorts of controls you'd normally have for a scientific experiment. Now, I have to admit, and I'm not proud of this, but this is the fact, I went into that study with a very strong bias against even the hope that we would see anything, because I knew the literature in this area was not very good, but furthermore, it basically didn't show anything repeatable. You might see something statistically significant at a p, 0.05 level probability, but all that means is that 1 out of 20 experiments is going to tell you something really did happen when it didn't. So I wasn't very impressed by the literature. And I told them, I said, well, let's not rush into this. Give me some time to actually study the literature in detail before we do the experiments. And I thought it would take me a couple of weeks, and it took me about 4 months because I was able to fortunately, I was at University of Michigan at that time, where they have a spectacular library system, and I was able to get copies of every paper that had ever been published on the use of electromagnetic stimulation to promote tissue growth, heal injury, and more recently to have effects on gene expression. So I think it was about 667 papers total that I actually remember reviewing in detail, and I had big tables of, I was going to write a review paper on this, and I had big tables of, what people had done and the different sorts of interventions they had done and everything, so I felt like, okay, we've got a great jumping off place here. I kind of feel like I understand the literature. And by the way, I was not very impressed. The literature in the field in general is kind of low quality when compared to the science that you see in things like molecular biology. Very often in electromagnetic research, you'll see a very important paper comes out, they make very important claims, and then you never see anybody build on that paper, you never see the original authors replicate the paper, and that kind of raises the red flags, right? So I went into this very cautious, and I thought, well, I'm going to try to show once and for all whether or not anything is happening. So I sat down with the guys at NASA again, and I said, look, I really think you're wasting your time here. I've reviewed the literature, and I don't think there's any basis from which to do this experiment. Do you still want to proceed? And they said, yeah, we have a little bit of funding for it. Let's go ahead and go forward. And then critically, I asked them, what exactly would you like to do? And so a lot of people ask this question, and I'm glad that you're giving me the opportunity to sort of just say it. I said, what kind of thing do you want to do? And they said, well, we don't know. I said, like, what kind of frequency do you want to use? What kind of waveform do you want to use? And their answer was, we don't know. And the technician who ran the experiment, the only input he had was, he said, well, let's try 10 hertz because I've seen that a lot in the literature. 10 hertz. Well, that's, it was just a guess. And he said he had seen it a lot, and I had seen it in the literature too, with a lot of other things. Now, let me make a sort of a scientific editorial comment on this. Since this time, many years later, I've actually calculated the number of different PEMF variations there are. And it depends a lot on what you think is different. I mean, would you say that 11 hertz is different from 10 hertz? How much different does it have to be different? But I've actually posted this online, and Pat, I'll send this link to you. If you actually put in whatever parameters you're interested in, I've got a calculator on Excel. It'll tell you how many different PEMF parameters combinations there are. And if you use just reasonable numbers, you never believe this, but it's something like a quadrillion different possible PEMF parameters that you could use. If you assume 10% difference is a difference, which by the way is based on the FDA's ruling, more or less, that any significant change in the parameters constitutes a different device and would have to be, approved separately from the beginning. So if you changed from 10 hertz to 11 hertz, the FDA would say that's a different device. You have to go back through the approval process. So if you do that, the numbers come out to like many trillions or quadrillions. And what that means is that for every different chemical on Earth, and there's only, depending on who you talk to, maybe 800,000 or 8 million, depending on who you talk to and what constitutes a different chemical. There's like 1 million different ways to do PEMF. So I'm sort of a numbers guy. I'm an engineer. Taking a wild guess is a pretty bad place to start. I mean, does anyone disagree with that? And if you're interested in this, I'll go ahead and send you. If you want, Pat, and you can post this on, because I know you've got a research place on your webpage. You can post this calculator, and if people want to see how big that number is, it's shocking, but it's there, and I left the formulas and everything. You can just see how it's calculated. So, right. I said, I am not going to just take a wild guess. We're going to do this systematically. And let me just ask Pat, is this too much detail, or do you think this is interesting to people?
I think it's very interesting. I mean,
we may as well go through this once, right?
Yeah, go right ahead.
Yeah, we may as well go through this once and kind of get it in the record, and hopefully people will embrace it, because I think there's value to it. So at the time, I didn't know it was that big, but I knew it was a big number, because just on the back of an envelope, literally, at a Holiday Inn at NASA, I was like, man, this is big. You can't just guess. At the time, I figured you have about the same chances of winning the lotto as you would at guessing the right parameters for PEMF if you just guessed them randomly. Well, it turns out there's a lot of things that temper that, because 10 hertz is probably not different from 11 hertz biologically. There's pretty broad ranges over which you'd expect it to work. But at the time, it was a very big problem, and frankly, the literature was not helpful, because any sort of general type of PEMF that you could imagine, there was some support for it in the literature. And the other problem with scientific literature is that you cannot publish negative results. So say, Pat, that I published something and said, hey, 10 hertz works, and then you replicated my experiment exactly, but were not able to show that it worked. You couldn't publish that. So the scientific literature, even though your work might have been just as good as mine, you're only hearing one voice. You're only hearing the voice of people who say, hey, I did something new and different and it worked. And that's a huge, massive failing in our science. We need to be able to say, hey, I tried to do that and it didn't work. And when you look in scientific fields where people do that, like astronomy and physics, the fields are extremely robust and they march forward very quickly because you hear both voices. If you look in fields where negative results are not publishable, like in medicine, biology, things don't go so fast, especially in medicine. You can only publish stuff that, that works. You can't publish stuff that says no. So I thought, okay, well, pardon me?
I had no idea.
Isn't it amazing? Isn't it amazing? So you're not hearing that whole other voice that says, wait a second, hold on. I did exactly what you said and it didn't work. That's not in the literature. So of the 6, and I figure for every paper that I found, there was probably somebody else who tried it and didn't get anything to work and couldn't publish it. Right? You think about it that way, maybe there was more than one. So there's a huge amount of information out there that's just lost. Right? So since I've got a chance to tell people about this, I appreciated that fact back in the late 90s, and I started actually talking to people who did this kind of research. Every single person I talked to, if I could visit their lab, I went and visited their lab so that I could talk to them and see what they were doing and get a sense for it. Every single one of them said, I published this paper and I got this result, and then I redid the experiment and I did it better and I got a negative result, but I couldn't publish it. So I know for a fact there's this vast amount of wisdom and knowledge that's just gone. It's impenetrable. So unless you're a professor like me who's willing to go visit people's labs and talk to them and invest in that, you can't possibly know this information, right? So this is something where I'm happy to answer these questions. It's not that I'm some super smart guy. I just happen to have collected this information over the last 20 years. It's probably not available anywhere else, right? And I mean, I've talked to people who've published books on this and people who've published important papers and all that kind of stuff. So we did the NASA experiments. And the way that I structured them was to break them into 5 different categories of different basic types of electromagnetic waves. Pretty much, they mapped pretty much with, does a sinusoid work, yes or no? Does a triangle wave work? Yes or no? Does a square wave work? Yes or no? Does a narrow square wave, sort of a trapezoidal wave, work? Yes or no? Does a fixed magnet work? Yes or no? We did the experiment. It was literally double blind. I mean, even on the device, I didn't even label the device. I calibrated it very carefully, traceable back to a primary standard at National Bureau of Standards. I knew what the magnetic field, I knew everything. But then when I labeled it, the label on the device was very cryptic, A, B, C, D, 1, 2, 3, 4. And they actually got kind of angry at me at NASA. I got a nasty phone call from a guy saying, you got to tell us what we're doing. And my answer was, no, I don't. The agreement was you do a blind experiment. So guess what? You're doing a blind experiment. You don't like it? Send my stuff back. So they went ahead and did it. And then when I pulled out the key and analyzed their data, sure enough, there was a huge effect, but only for a certain class of waveforms. And I'm sure everybody's interested to know what that is. The answer is square waves. Anything with a sharp edge. Trapezoid, square waves, narrow square, anything with a sharp edge. The sinusoidal, we saw nothing. We saw nothing from a fixed magnet. We saw nothing from triangle wave or shallow trapezoidal. It had to be sharp edged, close to a square wave. And the interesting thing was that the very narrow square waves were doing about what the broad square waves were doing, so I was able to narrow it down. It's all about the edge. It's all about how quickly you turn on and turn off the magnetic field. That's the nugget. That's what really mattered. Okay? So I said, wow, this is really, really great, but I don't believe it, so let's do it again. So they got angry at me, and we went ahead and we did it again. And I had a lot of leverage because at this point the guy who was the technician, Tom Goodwin, who published the papers, was he had become my graduate student, and I was still up in Michigan. He was in Houston, but I was his advisor. So I had a lot of leverage on him, and I said, no, we're not going to dash to publication. We're going to do the experiment again. Did the experiment again, found that something on the order of 100 genes were upregulated, a similar number were downregulated. Most of the genes related that were affected were related to growth and development, making extracellular matrix proteins, that sort of thing. So we got the same result again on a second repeat of the experiment, re-scrambled, re-blinded. So then I thought to myself, okay, I was a skeptic, but there's probably something here, right? So that was kind of the good news, and we got funding from DARPA, which is the Defense Advanced Research Projects Agency. They're the same people who put the money in to make stealth and to make the internet, so they try to stay 20 years out in front of everybody. So they were putting a little bit of money into this. We got a little bit of money. We did the experiments. Interestingly, and this is kind of where the story gets sort of sad, the technician who was running the experiments at NASA said, okay, it was his idea, so he published it and patented it without including my name on it, which is why you don't see my name on the NASA patents and you don't see my name on the NASA publications. And this is a big no-no. You just don't do that scientifically, but somehow or another, he thought that it was okay. And it's not just me saying that either, because we've kind of had like a legal thing going on with NASA for like the last 20 years, and their lawyers agree with me. They've done a big, investigation, and in fact, they've changed the patents, and I now get royalty checks from NASA and everything for that. So the lawyers at NASA agree with me that that was done wrong. The patent office agrees with me, but the public record really doesn't include my name at all, which is a bit sad because I'm really the person who was driving, in fact, did all the device development. They didn't do any of it at NASA. I figured out what needed to be done. I designed it, built it, tested it, calibrated it, put it in a box, and sent it to them. So the kind of sad thing about this is that they did not place in the archival record a correct description of the experiment. So it would be impossible for someone scientifically to replicate it, which is a huge problem, and it greatly undermines the value of the science that was done there, which, until it was published, was really very good, in my opinion. It also undermines the value of the patents, because the patents don't contain the key elements of what made the device work. And I know they didn't understand it at NASA for two reasons. First of all, they didn't publish it correctly, and they didn't patent it correctly. And then when they started licensing this technology out to people to use for growing stem cells and other things, NASA was unable to transfer that technology to them because they didn't understand it. They had a device they didn't understand. What ended up happening was companies would take out a license from NASA, they'd argue with them for a year or two trying to get the technology, and eventually I would get a phone call And this happened 3 or 4 times where somebody, a CEO of a company, would say, well, the guys at NASA admitted that you were the one who invented this. Would you please help us? We took out a license. We can't do anything. So this has happened to me 3 or 4 times now. And I've helped a few companies that are interested in using the technology for developing, technologies for growing stem cells and different things. A number of people, and I've talked to Pat about this years ago and everything, a number of people have started with the NASA technology as it was published and as it was understood, and have built technologies around it. So when you get on the internet, you can find a lot of people who sell PEMF systems. They claim a lineage that goes back to NASA, but so far as I know, Pat's the only person who's talked to me about how these things work and how they're supposed to work, based upon the actual work that we really did at NASA, as opposed to the sort of partial and incomplete reporting of it. I can also say that as far as the PEMF devices for orthopedic uses for anyone, humans, horses, anyone, anywhere, I know none of them have licenses from NASA. So there really hasn't been a lot of effective technology transfer from NASA to any of the other competing devices, and I think this is kind of relevant. So that's kind of where I'm at. I've been involved in this. I continue to develop the core technology. I continue to try to perfect it. I've run a number of independent studies at independent laboratories. I have a number of ongoing studies. Right now I'm trying to understand the basic cell biology of how is it that cells can detect this signal. I have several hypotheses as to what the exact mechanism is. I've been working on it for a while, but I've been doing it kind of, below the radar. So I don't publish it a lot. I had a doctoral student publish some of our thoughts on it a year or two ago when he finished his dissertation, I guess about a year and a half ago. But that's kind of where I'm at on it. So I'm, essentially an independent scientist continuing to do research in this area, talking to anybody who's interested in it. But I would say I'm quite confident in saying there's a lot of misinformation and a lot of disinformation on the internet about where this technology comes from, and right down to exactly what is the technology, exactly how does it work, just as an electronic circuit, and it's not well understood, unless people ask me. So
okay.
There it is. I guess that's the whole story.
No, and it's a good story. It was very interesting, and I thank you so much for sharing it with us. And that kind of leads me to, and you alluded to this in your story as you were going, you were very skeptical coming in. You didn't believe that it would do what people thought it might do, and your end result is it worked.
Absolutely, absolutely. I may be, I sort of pride myself on this, I may be the only person who's really been involved for a long period of time in this field who really started off robustly skeptical. And that's where you get the best science. I wasn't trying to prove that it worked. I was kind of biased against it. I was trying to prove that it didn't work so we could kind of put it to bed.
Right.
And so I did really, really hard, incisive experiments. And those were the ones that really supported that it does work.
Right. That's great. Thank you very much, Doctor. So, folks, if you have some questions, I notice that there are questions in the chat box at this point in time. Lane, why don't you bring something up and give us a question?
Eileen, I hope I'm not butchering your name.
And we'll see where we are on it.
Okay. Her hips are out. She suspects that her hips are out of alignment. This may be a good question for Dr. Jerry. She suspects that her hips are out of alignment and she's having really bad pain with it. Do you think that the machine would work for something like that for her?
Let's start. Go ahead, Jerry, and then we'll let Bob chime in.
Okay.
Yeah. What I find with hips, I mean, everybody has a definition of what a hip is. Is it the actual socket, or is it in the sacroiliac joint? So it all depends on where they're talking about the hip, and then is it the joint versus the muscle? And I can tell you that the PEMF definitely works on a muscle issue. If it is a misalignment as far as what we call a subluxation, the combination of getting it adjusted and using the PEMF over the inflamed area definitely helps.
Great.
Bob, what are your thoughts?
Chime in if you'd like me to.
Sure.
I'd support what Dr. Jerry said, basically. that I've done 2 independent studies at independent research laboratories on this technology, and both of them showed that there was a very, very potent effect on reducing inflammation. In fact, I was told by the director for inflammation studies from the research lab, which is independent, and I had no ability to do anything to direct the data one way or the other, because they do studies for pharmaceutical companies. They do drug discovery studies for pharmaceutical companies that become part of their FDA portfolio, so it's very tightly controlled. But the director of the inflammatory studies called me on the phone and said, we won't put this in the official report, but we've tested most of the PEMF electrostim devices out there, and none of them really had a very significant effect on inflammation. However, the devices that I sent to them, which are a much more advanced version of what we used at NASA, he said they had an unbelievably large effect, and it was almost immediate. And he said they basically couldn't believe it, and they thought it was very exciting. So we actually ran a second experiment, right? Because I remained skeptical, and we got similar results. So I can say for sure, when Dr. Jerry's saying it's reducing inflammation, we know it does that, and we know it does that very quickly, in an order of minutes after you start applying it, and we know it does it very robustly. And I can put a number on robustly. It gives you about 60 to 65% the reduction in inflammation that you would get if you took a megadose of dexamethasone, which is a steroid that's known to strongly suppress inflammation. But of course, with PEMF, you don't have the side effects and all that other sort of drug stuff that's involved. So going back to support what he said, is it's the data really strongly support that assertion that you quickly and significantly get reduced inflammation.
Thank you, Bob. And that's exactly what Michael always says. We're not necessarily a pain relief device. We're an inflammation reduction device, which relieves pain.
Yeah, it's very interesting when you put it that way, because part of the reason I was so skeptical, as you know, Pat, because we've talked about this, people use this kind of technology for a lot of very different complaints, a lot of very different injuries, things that they just don't really seem to have a lot in common except for inflammation, right? So people are like, well, why should it reduce pain, and why should it accelerate healing, and why should it do these other things? And a lot of that it does, and a lot of that is simply because it seems to really cut down on pathologic inflammation, and then the other processes in the body just work better. And I hear from chiropractors all the time, and maybe Dr. Jerry could comment on this, but the adjustments that they use, they just work better if you use it with TVEMF, because the adjustment stays longer. It's like the tissue's not inflamed and kind of pushing itself back out to a bad position as much. I hear this all the time, and talking to chiropractors, the mechanism that we most often discuss is, it's letting the tissues get back to the size and shape they should be. So when you make your adjustments and you make other adjustments to like diet and activity, they're much more effective, right? So it's kind of a part of a big treatment picture. It lets you get back to a normal state sooner, so that all the other things you're doing will be more effective.
Thank you very much. Michael, did you have a question or something? Yes, great.
I'm interested in, you say a square wave, so a high slew rate waveform. Mm-hmm. What is the ratio of on to off time that seems to work, or does it matter?
It actually matters a lot, and it matters a lot in 2 areas. One of them is I don't think the DC. Let me be specific, so for everybody who's listening, because I appreciate the fact that not everybody has a PhD in engineering or physics. So I'll try not to use too much shorthand. So DC magnet is like you're just holding a magnet there, and it's DC means steady, direct current, a steady field. And as far as I could tell, and I did a lot of experiments myself in addition to what we did at NASA, I couldn't see any biological effects. So you do have to vary the magnetic field over time. And so you kind of ask 2 questions. One of them is, what percentage of the time does it have to be on versus the time that it's off? So what's the ratio of that? And when I was designing the waveforms, I was basing it upon a lot of measurements I had done on animals during early stages of development and recovery from injury, post-surgical recovery. So questions like, when muscle twitches in an embryonic chick, is that helping bone development? Turns out that's critical for bone development. And, sort of how does the muscle twitch and how does it act during these critical stages of development and tissue growth and everything. So I did a lot of instrumentation development to answer those questions directly. I also did some direct measurements on how tissues respond to different pulse widths. And what I found for most musculoskeletal tissues is that if it's on at least 50 or 60 microseconds, it can then be off for a long period of time. So I usually, I recommend a pulse width of about 100 microseconds, which will capture just about everybody with individual variability. And then it can be off 99.8% of the time. So this has a couple of very important technical consequences. One of them is it allows you to make a system, and the thing that's interesting is if you put a square wave that's on 50% of the time and has the same slew rate, the same steepness of the trapezoidal wave, let me point right at the camera, the same steepness of the trapezoidal wave for a wide square wave as it does for a very, very narrow pulse, you get the same biological effect for the very narrow pulse. But that wide square wave does two things. First of all, it puts a lot of energy into the tissue that doesn't need to be there because it's maintaining a magnetic field. And secondly, it sucks a lot of energy from whatever's powering your system. So one of the things you want to do is make that pulse width as narrow as you can. And I've spent 2 decades figuring out what that number is, and that number is about 100 microseconds. I've run a lot of experiments. If you go much below 50 or 60 microseconds, you lose the biological effect. So you have to have a slew rate. It has to be a certain slope, and that slope has to be turned on for a certain amount of time. Once you finish that slope, it kind of doesn't matter if you stay there for very long at all. What then matters is how fast this downgoing slope is so that you return to zero. And so the answer to your first question, what's the ratio, you can get a very much the same biological effect if you cut out 99.8% of the energy that you have stuck in between the two edges. And that's what I do, and that's where I've done, all my experiments for the last 6 or 7 years have been in that range. And in fact, that's one of those things that wasn't published at NASA. That's something that should have been published because we did the experiment there with narrow pulses and wide pulses, and that's something that was known, but because of the way it was published, it wasn't conveyed.
We have several questions.
Let's Michael, can you give us your feelings of what Doc said and where we are in that same configuration?
Well, actually, I have a question towards that end. So for a 100 microsecond impulse, that means it's a relatively low voltage and a relatively high capacitance that's being dumped in the coil.
That's right, exactly. And so the devices that I design, that's exactly what I do. And so you have to have a low, I'm gonna go real quick because I know I'm talking to an engineer here. You have to have a low impedance output, and you have to have a capacitive dump that allows you to do that at the right speed. And so you need to build a tuned system. It's sort of like making a piano. Like you can make a great piano, but then you got to tune it, right? And so I've spent a lot of time tuning these systems, and I can tell you, you want to be right in the sweet spot on the slew rate. And if you guys are interested, I can tell you about a completely different study where I discovered and I was able to verify what that slew rate is. I mean, if you're interested, I can tell you.
We are certainly interested in
Oh,
Michael,
sorry,
you have one more follow-up?
So is there range voltages of the power supply delivered to the coil that seems to work best? And is there a range of capacitances that you're charging and discharging that seems to work best?
Those are all pretty tight technical details, and the answer is absolutely yes. And I'm happy to tell you what those numbers are. Maybe your listeners wouldn't be too interested, but what I can tell you I did is that about 3 years ago I did a component sensitivity analysis because I was getting ready to think about going to the FDA, as well as I was trying to make the most efficient system. So I was literally tuning the hardware. It's sort of like going in and making a piano, and every screw and every nut and every bolt and every piece of wood and every dab of glue, you figure out exactly how much you want to use, right? So I actually did a sensitivity analysis on every single component in my circuit, and I found that there is, in fact, a range of capacitances, and for each of the components, I found what was the best range to give me the absolute highest level of efficiency while keeping what I knew was the necessary biologic signal so that I could have a system. And as Pat knows, I mean, I design these things and they, run off of small batteries for a long period of time because there's almost no electrical waste in the system. We talk about this all the time. And one of the things I did was I actually used a thermal imaging camera on the circuit, and wherever I saw a hot component, that meant I was wasting energy, right? So I literally went through and did a detailed sensitivity analysis. And one of the things you have to understand about me, maybe I'm OCD a little bit or something, a little obsessive compulsive, but my background in engineering is that I worked on strategic weapons for a while, for shooting down nuclear weapons that are in orbit, which never happened, but back during the Cold War, that's what I did. So I'm a little bit inclined to make absolutely positively sure I've got everything right, and that's how I went about designing the systems that I use now. So there's no such thing in any system that I've designed. There's no such thing as a sort of just an arbitrary guess on a component. I mean, I know exactly what range works, and I even checked the differences in different manufacturers, because as you know, as an engineer, a lot of the components are not exactly what they say they are in the specification sheet. So I think if you're going to make a good product, those are the kinds of questions you have to ask, and I'm always happy to talk to people about how to do that best.
Thank you very much. Yes.
You want me to ask those? Okay, Dr. Alice Maybank asked for Dr. Dennis. Online there is naturally occurring PEMF fields and that they are essential for life. Were you aware of these claims when you started your research, and can you comment on this premise?
Yeah, I'd love to talk about that a little bit. It's kind of a little bit negative. You guys want me to tell you the truth? I'm happy to do that. Oops, I'm sorry. Sorry about that. I had my cell phone turned off here, and I thought that was okay. So let me tell you the truth about that. There are many claims on the internet that that PEMF fields are essential for life, and that people have even given webinars about this, where NASA did experiments when they were going around in the space station, and they measured magnetic fields, and they found that if you're not in these magnetic fields, your body just falls apart really fast and everything like that, okay? Let me tell you the truth. So far as I know, that is a complete myth. Let me tell you how I know that. For quite a number of years, I was the go-to guy externally for NASA to talk about biologic effects of electromagnetic fields. The laboratory in which this research was done was the laboratory of Dr. David Wolf, who's a personal friend of mine. Dr. Wolf has a degree in electrical engineering, and he's also a medical doctor. Dr. Wolf was on the Mir space station at the time we were doing the experiments in his laboratory. Dr. Wolf, for a long time, held the U.S. record for duration in space. He was on the Mir space station for 4.5 months. He still suffers a little bit with some, it's publicly known, a little bit of bone loss that you get from being up there for that many months. And he and I have talked about this. Is there any truth to this? If anyone at NASA would know that NASA had done research, medical research, on electromagnetic fields and their importance for biologic systems living off-planet, it would be Dave Wolf. And Dave says to me, I never heard of it. And if anybody outside of NASA, who at the time these studies were supposedly done, would have known something about it, would probably have been me, or I would have been one of the people. I was actively engaged and working as a consultant. They certainly would have asked me about it, I think. I think that, anybody that I've asked and talked to, I've talked to other astronauts about it who are medical doctors and veterinarians. There's no basis in fact for that assertion, and it's my personal belief that that's a fabrication that's been made by people on the internet to further expand the NASA story, because there is this kind of murky background, and fortunately I have a chance to kind of give my side of the story. My side of the story is supported by legal documents from NASA and from Patent and Trademark Office and everything else. Other people will have different stories. I would recommend to the reader and the listener that they demand source material. But I really think that the people who've started this discussion were doing so trying to add credibility to the notion, hey, NASA's already involved in this, and if we sort of spin the tale a little bit, maybe we can have NASA telling everybody you need to have these things for health. NASA has no such data, so far as I know.
That's very interesting.
Thank you very much. Elaine?
Okay, Lee asked, how does PEMF affect the C neutral pathway?
The neural pathway.
Neural, sorry, I read that wrong. My apologies.
C neural pathway?
Yes.
You know, this is my favorite answer. I have no idea. I have absolutely no idea.
So is he talking about a class C fiber that regulates
That's what
pain?
I think. That was my
Well, what we know as far as how the pain gate cycle works is you end up with some sort of an infarct or injury, and then from that you have like a COX-1, COX-2, COX-3 system that turns into prostaglandins, and then that is basically what causes the pain. And science tried to come in and do a COX-2 inhibitor like Vioxx and Celebrex, but they only got half the equation right because they eliminated the COX but not the LOX, and that's what was causing people to stroke out. And so things that happen naturally, like fish oil, it goes in and it helps eliminate both of those to eliminate pain. So I can only imagine that with the PEMF, that it has something to do with the production of the prostaglandins as far as reducing inflammation. But as far as at the cellular level, it's really tough to see because it has to be an in vivo study, which is really tough to put a human being under a microscope and see exactly what goes on.
So let me expound upon that because I think that's the right answer. What I'm doing now is I have 2 different studies that I've initiated to try to figure out what the cellular mechanism is for signaling using PEMF. And they're being done at laboratories outside of my lab, and I'm supporting them technically so that they'll do the right kind of PEMF intervention. But the idea is we're trying to break up the signaling pathways, you know, into different groups so that we can start to say it is impacting this pathway or it's not impacting that pathway. Either these cytokines are involved or there's calcium signaling there. And in fact, my working hypothesis is that there's a not yet discovered membrane receptor for streaming currents of differential ionic charge. And the reason that hasn't been discovered is that patch clamping looks at it exactly orthogonal to the direction it would need to discover that. So I'm working with some people, including one of the students of the person who developed patch clamping down at the University of Houston now is where this person's at. And I've got a couple of labs going. So maybe a year or 2 from now we'll actually know what the signaling mechanisms are. I would say that I think, you know, backing up from your question a little bit, I think it's not just having an effect on excitable tissues, nerve and muscle. I think it's probably a well-conserved signaling mechanism that you see in many, many cell and tissue types. But I don't know. And so that's what's great about science. You know, it's great to have a good question like that and have a way to test it.
And what basically they're asking about is in the human body we'll have nerves, and on the ends of those nerves are certain receptors for certain types of systems, whereas a pain fiber is just a dead-ended system. And what we also have found out too is when there's an injury is that nerve will splay, so now you have 5 times more sensory of pain because of that area being injured, and it's a way, I think it's a coping mechanism for the body to tell you that there's a problem and to avoid using it so that you can help heal it better as well.
Well, you know, and it's possible that the signaling that's of interest in this specific case is upstream from that.
True.
Great, thank you very much. Great question and great response. I really appreciate that. There was another question that was asked, and I want to cover it because I want to be totally transparent how we approach PEMF, technology that Bob Dennis is talking about. And my answer to that, then I would like Bob to comment, and Michael can tell us where we're going with Magna Wave and the PEMF devices that he made.
So you guys are breaking up a little bit. Did you have a question for me, Pat?
Yeah, in just 1 second, Bob, I do have a question. So
yeah, you're breaking up a bit. I'm having trouble hearing.
I'm sorry. I'll have my mic to you, Elaine.
I can hear you. Just keep going.
Okay, so Bob will be right with you. But and Bob and I have talked about this a number of times, and he's researched our devices and certainly fine-combed our website and the things that we do talk about with regard to MagnaWave and Michael's PEMF devices. And that is that we are on course. Our signals are very fast. They quit, they start, they stop. They are of the design that Doctor talks about. We as a company are moving towards new technology, solid state technology that will allow us to better fine tune these signals that we deliver and how they are consumed by the body. Michael?
To have a 100 microsecond impulse, you would have to have a multi-hundred microfarad capacitor and probably a voltage of less than 100 volts just charging.
Yeah, and what I have is 1,000 microfarads. What works is between 470 and 1,000 microfarads, and the voltage that works is anywhere in the range of 28 to 38 volts. So you are correct.
Right, because
you have other things that you need to sort of factor in, like the impedance of your coils, and also there's another factor that most people tend to forget, which is to get the right magnetic slew rate, you have to energize, a magnetic field in space has a certain amount of energy, right? It's like pumping water into a pail. If you're pumping water at a certain rate into that pail, that's like your power for putting energy into a volume. If you make the pail twice the volume, but you're only putting energy in at the same power, the rate at which you're filling the pail is half as much. This is conservation of energy. So one of the factors that everyone seems to forget when they're designing these systems is that they have to energetically potentiate the volume that they're stimulating with the energy that they're putting through the coils. So it's a little bit more than just the slew rate to the coil. It's a little bit more than that. Like I say, I'm happy to sit down and discuss this with you, but I actually go straight to the answer. So I've actually built my own high-speed peak detecting magnetometers, which you can't buy. But I actually have a sensor that you put right in the coil, and it shows you right on an oscilloscope what the slew rate is of the magnetic field at any point of interest. So when I calibrate my systems, it uses this sensor. This sensor is calibrated and with a calibrated magnet. It's traceable to NIST. So I find myself, it's like when I want to invent, it's sort of like if I want to invent the mousetrap, I have to invent a way to make steel wire, and I have to invent a way to make pieces of wood, and I have to invent a way to make cheese too. It's like when you're making these devices, there's a whole lot of stuff that just hasn't been done. And all the instruments that you need, in my opinion, technically, to calibrate these devices properly, they just don't exist. You have to build them. Fortunately for me, I'm a electromechanical instrument designer, so a lot of my time goes into that. So a lot of the study and the data that you see, most of the work for me was really kind of upfront, just making sure that when I say we're using a trapezoidal wave and it has these kinds of characteristics, that I know that that's true and that I can prove it. And I believe that's at the core, the fundamental skepticism I started with, and the fact that I'm using good engineering principles to make sure that I'm measuring what I think I'm doing. What most people do is they'll calculate it. Oh, well, the magnetic field should be X. They never measure it. What almost everyone does, as far as I know, everyone does, is that they don't measure it with enough time domain resolution to be able to say, well, on the trapezoidal wave of the magnetic field, it was actually this slew rate, because there's a lot of things that can force you to deviate from theory quite significantly. It may simply be that a transistor that you're using, if you're going solid state, doesn't work exactly the way that transistor is supposed to work. So what I do is I calculate all that stuff and I get it sort of in the ballpark, but in the final analysis, I make absolutely sure that I'm taking the measurement. And when I went and talked to everybody in the various labs that would talk to me, when I studied the papers, when I went through all of this stuff, that was what was missing the most. It was a really careful characterization of exactly what they did in their experiment. So you see what I'm saying? That's the deficiency that we have in the literature. That seems to be the deficiency we have in a lot of these products, is that they're not well understood even from the one area where we could understand them completely, which is the engineering side. We may not understand the biology, but our excuse is it's very complicated, we didn't design it. But to the extent we don't understand the engineering of what we're doing, that's kind of our fault, right? I mean, because we can make these measurements, we can carefully do these things, and to the extent that the scientists and engineers don't do that, it kind of explains why something was working and all of a sudden now it's not working, you know?
Thanks, Bob. And I think that's excellent. Michael has a comment or a question he wants to answer at this time.
I know originally NASA selected 10 hertz rather arbitrarily. Was there studies done on other pulse rates or frequencies to see results?
Yeah, absolutely. And in fact, I've done some, and I found that 10 hertz it's like saying, how fast do you have to drive to get to the post office? Well, there's a whole range of speeds that are reasonable, right? One exact speed is, I think a lot of people make the mistake that you have to, there's this sort of like Teutonic obsession with precision. And biological systems aren't that way. I mean, every measurement I took was always, plus minus 20%, plus minus 30%. It's important to understand that. I'm not saying that out of being lazy or being imprecise because of lack of discipline. It's simply that biological systems have this variability. Like, exactly how many calories do you need to eat every day? Well, you don't eat exactly 2,200. There's variability. Exactly how many steps do you have to take? 10,000 a day to be healthy. Does that mean 11,000 is bad? Does that mean 9,500 is not enough? It turns out that biological systems, there's pretty smooth caps on these optimal frequencies. It's not like 9 hertz doesn't work and then 10 hertz is the sweet spot and then 11 hertz doesn't work. And this will explain something that I think is important to convey to you guys. People talk about Schumann resonance frequencies, somewhere around 7.82, 7.83 hertz. And people ask me, do Schumann resonance frequencies work? And my answer to them is that's the wrong question, because you're asking me, do they work because they're Schumann resonance frequencies? And my answer is they work because they're somewhere in the range of 1 or 2 to 25 hertz. They just are.
How about
it's a complete coincidence, right? So I've done studies on this, and I find that 10 hertz is probably just as good as 12, is probably just as good as 8. Now there are reasons for varying it, but it turns out frequency is not the most important thing. It's sort of like saying, if you measure the volume of the radio in your car, will that tell you how fast the car is moving? There might be a loose correlation. Louder music means the car is going faster, but it's not really the thing that tells you how fast the car is going. And frequency is probably one of the least important parameters for PEMF, just so long as you're in a range that makes physiologic sense, which is sort of a couple of hertz up to a couple of dozen hertz, in my opinion.
Thank you very much,
Oh, you're breaking up.
Bob.
Yes,
And I hope it's the same way to our listeners. And I guess the thing that me as a layman, I heard was that PEMF works. There are devices that might work quicker than other devices. There are devices that may be designed that don't work very well at all. But the thing is, we're on a track here that the important thing is to take a device that works and then continue to refine it to make it even better, so we can get a better result for our patients. I know that's where we are with Magna Wave and what Michael is doing. And I hope that just kind of maybe sums it up in a layman's type of term.
I think that's true, and I mean, you and I've talked about this a lot of times, and I think that's what's really needed. Now, when you look at most of the devices that are out there, I don't get any sense that they are doing that process. And so when they have a new product, it might just be a new box, a new label, a different color, but they haven't really sort of committed to figuring these things out. And the fact of the matter is, if you make a little bit of an improvement every year, you get a little bit better understanding. You make your engineering a little bit better. You make your understanding of the biology a little bit better. You add that up over 10 or 20 years, and then there's a huge gulf, right? So there's two problems with people who base their technology strictly on what was written by NASA. First of all, that was 20 years ago almost, and second of all, it was incomplete. So if that's the gospel that you're following, there's huge deficiencies. And Pat, it requires you to do what you guys have committed to doing, which is, listening to crazy mad scientists like me and, factoring in all the information. A lot of it is listening to the people who use your product. Does it work? And if all of a sudden it stops working, then that means you changed something you shouldn't have changed, and you got to kind of go back and fix it. If all of a sudden it's working a lot better, you want to know why. But in order to do both of those things, you have to understand your product really well. And I guess what I'm saying is it's just like the piano factory, right? If they don't have a person tuning the piano at the end of the line to make sure it's tuned, some of your, all your pianos may be exactly the same quality. They may be exactly the same piano with exactly the same workmanship, exactly the same, components. Some of them are going to come off the end of the line and they're going to be tuned properly and they're going to sound great. And some of them are going to come off the line and they're not going to be tuned properly and they're not going to sound great. And if you don't know about tuning pianos, you'll never figure out why that is. You see what I'm saying? I think the analogy is pretty strong. So you need to understand which parts of the technology really matter. And then you need to get control of those. And that's what matters. And I think you guys are doing it. That's why I'm perfectly happy to get on here and talk to you. There's a lot of people making these things, a lot of products. Honestly, I wouldn't lend my expertise in a public way to them because they would ask me questions that were leading and deceptive, and then they'd try to take what I said out of context and say, I know you're not going to do that. But, they're looking to get, rather than doing the work of making it work reliably, making it always a little bit better, they're doing the work of trying to spin doctor it, and I can't really help them.
Rock Bob.
Break it up.
Thank you very much. I really want to have you on. As you know, you and I have been talking for years about improving things and how to make things work better, and I certainly appreciate it. Jerry, any final thoughts from you, Dr. Dreesen?
It's been great listening to the whole process. I did a lot of reading. I studied some of the NASA things that came out, and be great that you could get your name put back in on those studies. I know kind of what that's like, where you get the carpet yanked out from underneath your feet after putting so much time and passion into it. The great thing too, as far as on the ramping, I guess a question that I have maybe in magnetics is if you can raise the power up, can you go the opposite direction, or do you always have to hit bottom? You can't go below that line on your square?
Well, that's a really interesting question, and that was the thing I was telling you. If you want to know that, I don't know if you guys want to go over time or something. I'm happy to talk to you, but I can tell you how I know what that sort of minimum threshold is, and it's because we ran a study at Texas A&M University on rabbits. And we did a critical defect in a rabbit ulna, which any surgeon can tell you, and most doctors can tell you, a critical defect is one that should never heal. So it's a really good model for, are you doing something that's going to cause healing where there otherwise would be no healing? And the answer is that below a certain threshold for the slew rate, if the square is a little, if the slew rate, the steepness of the slope is a little too shallow, it won't work. And the actual number below which you never want to go is 250 kilogauss per second. It just turns out that's the number. And so when we started doing the experiment, we were just barely above that threshold because the technology was quite primitive at the time. It was 2006, 2007. And we were in the 300 to 350 kilogauss per second range. How did I know that? I measured it. All right? Because of the way that the study was being conducted, they actually changed the study halfway through. They changed the coils. It was being run by a company, and I didn't have control over parts of it, unlike the NASA study. So they changed the design of the experiment, and as a result, they were trying to make the coils bigger, because everybody's always like, well, can you make the coils bigger so it covers the entire injury? So they were saying, well, the surgeons were concerned that it wasn't covering the entire defect, so they absolutely demanded larger coils. But like I was telling you, you got a bucket, you make a bucket twice as big, you fill it with the same hose, it takes twice as long to fill that bucket. So it's all about how fast you're filling the bucket with a magnetic field, okay, not water. And so when you make the bucket twice as big, the rate at which you're filling the bucket goes to half, and it turns out the biological effect vanished, all right? And I know at 200 kilogauss per second we saw nothing, and at about 320 kilogauss per second we saw a very robust biological effect. And that is, that's how I know that answer. And since then I've done a few experiments. So, I do know what that number should be. We didn't know that from the NASA data. That's nothing that should be that's nothing that should be contained in that information. There's no way for you to know unless you ran an experiment. This experiment's never been published because it was done privately for a company that had taken out a license from NASA to develop the technology. I knew about it because I did not conduct the experiment, but I built the equipment for it. So I knew the equipment was right, and I was involved in the experiment. So it's these sorts of things, and I'm trying to sort of collect all this information together. Maybe someday I'll write a book or something, and all 12 people who are really interested will read it. But it sort of explains all of these things. It's a kind of an interesting story about what's wrong with science and what's wrong with some motivation that people have. But it's there's a few of us out there. Pat's one of them, and his people. We're trying to do this right. And it takes a long time. We've been at it for, I know Pat's been at this for, 15, 16 years now. I've been at it for close to 20. It just takes a long time to get this right. And unfortunately, there's a lot of people out there who are not dedicated to doing it right. They just run out with a product and sell it. Some of these products, believe it or not, I've bought them. I analyze them with my measurement system. Bill Pollack actually published sort of a white paper on one of his web pages about how he actually came over with some of these devices. We tested them, and all of them were way off of what they were saying they did, and they were way below that minimum threshold for, slew rate. Now, maybe there was some other electromagnetic mechanism in the works. Maybe their stuff worked, but I can tell you as an engineer, their products didn't do what they said they did, and I can also tell you as a scientist, their products didn't do anything in the range that I know will have a biological effect. And you have to measure these things, right? And I'm pretty confident that they weren't doing that.
I have one more question to ask, unless you need to.
Let's take a couple more minutes. That's fine.
Yeah, I'm happy to give you as much time as you like.
Well, I want to try to keep.
I had a question because I'm using it. I'm using the product a lot on people that are in auto accidents with head injuries, and I know you're doing a lot of tissue samples. Have you had any kind of studies on Purkinje cells and with any kind of brain infarcts and that type of inflammation?
Well, it's interesting that you asked that question because I have a very complex answer to that. I actually have a completely different product, which you can read about. It's on the internet. It's called Cortical Metrics, and it's called Brain Gauge. And we actually were selected by GE and the NFL last year. We won the GE NFL Head Health Challenge. It's another one of these devices that I've designed. And we're now viewed by General Electric, the NFL, the United States Navy, and the U.S. Marine Corps as having the best technology for assessing brain injury from mechanical trauma. So that's this other product that has absolutely nothing to do with this. And so what I'm trying to do right now is negotiate with the Office of Naval Research, the ONR, to take the PEMF work that I'm doing right now on this stuff that we're talking about, combine it with this other technology, which is about 10,000 times as sensitive as any imaging technology, because it's hard to explain. You'd have to look it up on the webpage. But it uses highly precise somatosensory testing to test brain function. So when we're trying to merge these two things together so that I can actually intelligently answer the question that you just asked. But the answer is, I'm trying to answer it, but I can't answer it right now. But I have the tools to answer it, and it just kind of comes down to, can we get the right people behind doing the studies? And we'd like to do that kind of a study at the VA. And we actually have these devices. These cortical metrics devices are all over the world, and in Canada and South Korea and Europe and Asia, and they're used by a lot of universities to test athletes after they've had an incident. And we can detect head injury with about 98% accuracy, which is way past anything else. And so anyway, that's a whole other story. Maybe we can talk about that some other time. But I would like to be able to say a lot more about how PEMF relates to the process of healing injury in head injury. And I hope within a year or two to be able to answer that much more comprehensively, because I have the tools. I just haven't done the study.
Look forward to hearing it.
Yes, thank you, Bob. Again, and I think what Dr. Dreesen's going after is that he has seen some good, dramatic results in dealing with the neurological injuries and recovery and that type of thing. Is that correct, Dr. Dreesen?
I've had people that have had lost their jobs because of their brain injury. They just, they can't handle more than one thing at a time, and when 2 or 3 stress issues come up, they have a complete meltdown, and now they're able to actually get their feet underneath them and begin looking for work, feeling confident that they're not going to have a huge emotional episode.
And I'll say, sort of taking off my engineer and scientist hat and just sort of giving my opinion on this, because I'm so embedded in this with so many other people. Anecdotally, I hear exactly what you're telling me. So although I can't verify it with data, anecdotally I've heard several hundred times exactly what you just told me, is that, and my hypothesis would be, yeah, it does reduce swelling, it allows your brain to heal. When people ask me about it, that's the opinion I give. But I don't have any data to support it other than anecdotal data. And I'm not a clinician, so I don't really have a clinical opinion.
Thank you, Bob, and great association, Jerry. That's the reason for this call today, and this information is to see how we can improve and continuing to improve. Michael, you had one more comment?
So if you have a roughly 500 microfarad storage capacitor and you're charging it to 30 volts and your impedance is low in your output coil, that would tend to indicate a peak magnetic energy in the 5 to 30 Gauss range. Is that accurate?
No, actually, you can do a lot more than that. It can be quite a bit higher than that. So, I mean, you can sort of calculate it. You can back calculate it. If you do, if you say the minimum threshold, and I'll just calculate it here while we're talking, is 250,000. That would be 250 kilogauss per second, and it's very close to that actually for the minimum threshold. Times 0.0001. Yeah, so you'd get, as a minimum, you'd get something like 25 to 30 Gauss, but that's sort of at the threshold, right? And I think that the best therapeutic effect is 2 to 4 times that, roughly, from what I've seen in animal studies where I can actually quantify therapeutic effect. So when we did a dose response study, our peak, as you say, the peak magnetic fields are in this sort of range of because you're dividing 250 kilogauss by 10,000, right? Roughly, is I think the calculation you did, which is what I just did. That you start to see your biologic effect there, but that really doubling to quadrupling that is really where you want to be. But still, you're only talking about peak fields that would be in the sort of range of 120 to maybe 200 Gauss. It's not really that big of a magnetic field in terms of its peak. But once again, I don't believe it's the peak that matters. What I believe is the first time derivative. For those people who know, it's the slope, right, of the trapezoid. So it's the first time derivative that you got to have right. And the peak is simply a consequence of the first time derivative and how long you keep it turned on, right?
So I tell you, I really want to stay within as close as we can with our time constraints, because people play this in their car or they'll watch it and we want to keep their attention. And I certainly believe, ladies and gentlemen who've been so kind to stay with us and watch and listen, if you'd like to have more of this, we can get further in depth on future programs, which is certainly enjoyable. And I'm sure the scientific minds out there, of which I encounter all the time, people want to know, how do it know? How does it work? And we certainly want to go there and get that information. So, Dr. Dennis, I appreciate you being with us today. Jerry Dreesen, thank you for coming at it from the standpoint of a chiropractor. Michael Davis, thank you for your input as a manufacturer and developer of these types of pieces of equipment. It's certainly a learning experience for me, which has been from the first day I got involved with this type of technology, and it's just a desire for me to put it out there and help people feel better. Elaine, thank you so much for helping moderate the program. Ladies and gentlemen, please join us again next week, 1 o'clock Eastern, for the Magna Wellness TV program. If you have a question or if you have a program you'd like to see us bring.com, and we'll get at that and bring the programs that you want to have and enjoy with alternative medicine and development of health with PEMF. Doctor, thank you so much. Both doctors on, and Michael and Elaine. Ladies and gentlemen, thank you. Have a great day. Bye.
Thank you.